Welcome to AminAcademy.com. In astronomy, regarding motion of satellites, let us do some solving problem with some discussion. Here, first we'll discuss about orbital speed equation. That means that satellite, how fast it move around the Earth, we can calculate now. Consider a satellite with mass M, that is M satellite, mass of the satellite is capital M, obtaining a central body with a mass of M central. Suppose central body is here, our Earth, that is M central. The central body could be a planet, the sun, or some other large mass capable of causing the sufficient acceleration on a less massive nearby object. If the satellite moves in circular motion, then the net centripetal force acting upon this orbiting satellite is given by the relationship. This is a F net force, that is centripetal force, is equal mass of satellite into V square divided by R. That is, we can say mv square by R. This net centripetal force is the result of the gravitational force that attracts the satellite towards the central body and can be represented as gravitational force is capital G, thus universal gravitational constant G into mass of satellite into mass of central body, that is our Earth, divided by R square. Then we can say simply F equal G m1 m2 by R square. Since both forces are equal, that is gravitational force and net force, both are equal, by equating this expression we get m sat v squared by R is equal G into m sat, that is mass of the satellite in m central body, divided by R squared. Then from this relation, that is here mv squared by R, here G m1 m2 by R squared, then we can get V square equal to G into mass of the central body divided by R. Then V equal, this is the final formula for velocity of the satellite orbiting, that is V equal square root of G into mass of central body divided by R. Here, if we substitute, the value of G is 6.673 into 10 raised to minus 11 Newton meter square per kg square. That M central is the mass of the central body about which the satellite orbits, here our Earth, and R is the radius of the orbit of the satellite. This is the formula for velocity of the satellite. Then, what is the acceleration equation? Similar reasoning can be used to determine the equation of the acceleration of our satellite, that is expressed in terms of the masses and radius of the orbit. Look at here, G, gravitational constant G equal to capital G into mass of the central body divided by R square. Thus, the acceleration of a satellite in a circular motion about some central body is given by the following equation: A equal G into mass of the central body divided by R square. Here, this is the acceleration equation, where G is the constant 6.673 into 10 raised to minus 11 Newton meter square per kg square. Mass of the central body is the mass of the central body, here our Earth, and R is the average radius of the orbit for the satellite. Now, this is the acceleration equation. Next one, orbital period. The final equation that is useful in describing the motion of the satellite is Newton's form of Kepler's third law. Then from here, the relation, look at here, T square over R cube equal 4 pi square over G into mass of the central body. Here T square time period, square of the time period divided by the radius of the central body, that is R cube of that radius, equals 4 pi square divided by G into M of the central body. This is the relation from Kepler's equation and Newton's formula, where t is the time period and r is the average radius of the orbit for the satellite. G, the constant given. Therefore, here these are the three important relations to calculation we can use for calculation of the satellite motion. From this equation, we can solve some problems also. Thanks for physicsclassroom.com. Now let us do some example problem regarding this concept. Here, look at this one example problem. A satellite wishes to orbit the Earth, that is Earth satellite, at a height of 100 kilometer, approximately 60 miles, 100 kilometers above the surface of the Earth. Determine the speed, acceleration, and orbital period of the satellites. Given mass of the Earth is given 5.98 in 10 raised to 24 kg. Radius of the Earth is 6.37 into 10 raised to 6 meter. Now the given things, look at here, r, the radius, that orbital radius is the radius of the Earth plus height. Here radius of the Earth plus height, that is r plus h, which is equal 6.67 into 10 raised to power 6. Then that is given total from the center of the Earth to the radius point. That is mass of the Earth is given and g is given. From that we have to find velocity, acceleration, and time period, means time taken for one rotation. So we are using the formulas v equal to square root of g into mass of the central body divided by r. So we have v equals square root of this, putting these values, that is g is 6.673 into 10 raised to minus 11, and mass of the central body, that is Earth mass, is 5.98 into 10 raised to 24 kg divided by radius of the orbital, that is orbital radius is 6.47 into 10 raised to 6 meter. From this, by using this calculation, using calculator, we can get v equal 7.85 into 10 raised to 3 meter per second. Such a high, that velocity is given. The acceleration can be found from the other equation. Acceleration is, we discussed before, g into m central divided by r square. Then acceleration is v squared by r. So equation 1 was derived above already, and equation 2 is general equation for the circular motion. So g equal a equal to g into mass central divided by r square. By using these values, we will get a equal 9.53 meter per second square. Here, observe this is 9.53 is little bit less than the gravity constant 9.81. Observe that the acceleration is slightly less than 9.8 meter per second square, value expected on Earth's surface. The increased distance from the center of the Earth lowers the value of g. That means if you go beyond the Earth, that g value is reducing. Finally, time period equation is t square over r cube equal 4 pi square g into m central. That is mass of the central body. Using the values t, from this we can get it t equal 4 pi square over g into m into r cube. That is t square. Then we have to find first t square, and after the t, that using the square root of these values, final values, will get t equal 5176 seconds, nearly about 1.44 hours. Time period for one rotation 1.44 hours. Next, practice problem. The period of the moon is approximately 27.2 days. And converting seconds, it is 2.35 into 10 raised to 6 seconds. Determine the radius of the moon's orbit and the orbital speed of the moon. Given mass of the Earth is here, mass or radius of the Earth is given. So t, time period, is given mass of the earth is given and g is given by using this relation t square by r cube equal 4 pi squared over g into mass of the central body. So by using these values we are getting r. From this r cube equal to t square g m over 4 pi square. Find r cube, then cubic root of that values gives radius of the radius can be determined as the following. This cubic root of these values gives radius is 3.82 10 power 8. The orbit here we have to calculate, then determine the radius of the moon's orbit. Radius of the moon's orbit is here 3.82 into 10 raised to 8 meter. Next, orbital speed of the satellite can be computed from either of the following equation. V equals square root of g into m central body over r, or v equal to 2 pi r by t. Both equation you can use it. From that, v value is 1.02 into 10 raised to 3 meter per second. Here, geosynchronous satellite is a satellite that orbits the Earth with an orbital period of 24 hours. That means Earth's orbital period is 24 hours. The same, the satellite also moves with one round as 24 hours. It's called geosynchronous satellite, thus matching the period of the Earth's rotational motion. The special class of the geosynchronous satellite is a geostationary satellite. Geostationary satellite orbit the Earth in 24 hours along an orbital path that is parallel to an imaginary plan drawn through the Earth's equator. Such a satellite appears permanently fixed. It looks fixed above the same location on the Earth. If a geostationary satellite wishes to orbit the Earth in 24 hours, then how high above the Earth's surface must be located? That means geosynchronous satellite must be how much it high from the Earth's surface to be a always stationary with its rotation. That means on ordinary it focuses the same point. So given things, time period is given this because we are converting 24 hours into seconds here. Mass of the Earth is given, radius of the Earth is given, and g is 6 point, the radius of the position of the satellite from the center of the Earth here. Then g equal to given this, look at your figure, this r orbit is equal to r Earth plus height. This height you have to find. Here we know that t squared by r cube is this relation. From that, then we can get r cube is 7.54 into 10 raised to 24 meter cube. By taking the cubic root, it gives radius is 4.23 into 10 power 7 meter. The radius of the orbit indicates the distance that the satellite is from the center of the Earth. Therefore, we have to subtract this here, subtract the Earth radius, we can get it the height. That means from the surface of the Earth, how high that geocentric satellite position. That is equal to 3.59 into 10 raised to 7 meter above the surface of the Earth. So the height of the satellite is 3.59 into 10 raised to 7 meter. So thanks for www.physicsclassroom.com. We have done. Please subscribe our YouTube channel.